So this is the conclusion of third module. Third module, you should be able to, it's completely design of FIR filters. First thing, you should be able to compare IAR and FIR filter, right? So we have already discussed that thing. Next is the design of FIR filters. Mainly you have three methods to discuss. First one is Fourier series method. Fourier series method is also referred as this designing using rectangular window. So I will just conclude the method. First thing is HDF, capital HD will be given to you, desired response. You have to take the inverse Fourier series. So you will get, say, HD of n. And the problem with that is you will have infinite terms in that. So you can truncate it using rectangular window or directly from n minus 1 by 2 to plus n minus 1 by 2. So you can do that or 0 to n minus 1, whatever it is. You can do that truncation. Means minus 5 to 5, minus 7 to 7, depending upon the number of taps, right? So after truncating, the problem is the design is not realizable as it is having the negative part, so it's not non-causal. So the solution is you have to shift it by half units, say n minus 1 by 2 units, you have to right shift. So that is the last step. With these three steps, you will have achieved your design. So next thing is the problem with this rectangular window method is that you have abrupt truncation. You are making a sudden cut short at the time of windowing, means truncating. The problem with sudden truncation is that you will have ripples, you will have some oscillations in your frequency response. That is referred as Gibbs phenomena. And the solution to Gibbs phenomena is, instead of using abrupt truncation, you have to use windows with smooth truncation. Such windows are, examples are Hamming window and Hanning window that we have discussed. Hamming and Hanning window. So these are the main method in this module. And the last one is the frequency sampling method. The main advantage of this frequency sampling method is the last method. The main advantage of this particular method is that you will sample the frequency response just before designing, right? So as you are doing sampling with your response, you can say that the desired response, what I'm expecting, and the designed response, what I have achieved, right? Desired and designed. So the desired and designed response will be more or less the same at the points of sampling. So if you are concerned about certain frequencies, you should take care that while sampling, your concerned frequencies included in that sample. That must be included in that sample. So if that is not included, you have to change the sampling rate, and you should ensure that your frequencies of concerns are included in the points of sampling, so that at those concerned points, the desired and the designed response will be more or less similar, and you will be happy with the design, right? So that's the advantage of frequency sampling method. So you have a direct equation for that. You just want to make that table and directly write the equation. That's it. That is a frequency sampling method. So that's the then we made a comparison of different windows also, rectangular, Hamming, Hanning window, how window length, main lobe width, all are affected. So just go through that also. So that's enough with design of FIR filters. Then moving to fourth module, that was design of IAR filters. It's completely design of IAR filters. And even though the point of discussion is digital filter, the method is first we will design analog filter, then you will convert it to digital. Coming to IR filter, you will have infinite terms, infinite impulse response filter. You will have infinite terms. You have three types: Butterworth, Chebyshev type 1, Chebyshev type 2, and say elliptical also. And we have to discuss only on Butterworth as per the syllabus. So the ultimate target is designing Butterworth IAR digital filters, but we start with analog. We start with the analog filter design. So that was the first heading that we discussed: analog Butterworth filter. And even in that, first you have to design low pass filter, then you have to convert it to high pass, band stop, and so on. So the first heading was again the design of analog Butterworth low pass filter only. We designed the low pass filter. I will conclude the steps. Low pass filter, you have to design H of S, right? So the first step is to calculate the order. So from the given response, given parameters means you will have omega P, omega S, passband edge and stop band edge, then alpha P and alpha S. That is the ripples or tolerance in the passband and the stop band. So sometimes that may be expressed in dB. Okay, if not in dB, you have to convert in dB. The expressed value in dB is referred as alpha P and alpha S. Else they are 1 by root of 1 plus epsilon square and root of 1 by 1 by root of 1 plus lambda square. So accordingly, you have to manage all the terms initially to find alpha p, alpha s, or lambda, epsilon, those terms. We want lambda, epsilon, what else, omega p and omega, so that you can use the equation for order. First step is calculating order. N greater than or equal to n greater than or equal to log lambda by epsilon by log omega s by omega p, right? I think so. So that was the equation for order. എന്തെങ്കിലും മിസ്റ്റേക്സ് ഇടയ്ക്ക് ഉണ്ടെങ്കിൽ പറയാം കേട്ടോ, ഞാൻ ഓർക്കുന്നില്ല, കാണാൻ പറയണം. So that was order. So after calculating the order, what was the next step? You have to choose the appropriate transfer function from the table. So you had a table for the first order, second order, third order, fourth order, and so on. For low pass filters only, that table is particularly applicable for low pass filter and with cutoff frequency 1 radians per second. So next step is, after getting your h of s from use, depending upon the order you selected h of s, now you have to compute your cutoff frequency omega c equal, we can use two equations, omega p by epsilon raised to 1 by n or omega c by lambda raised, sorry, omega s by lambda raised to 1 by n. So if it is not specifically mentioned anything, you proceed with omega p by epsilon raised to 1 by n. Points to remember over there is monotonic in passband. You familiarized a term like that. Monotonic in passband means your omega p will be equal to omega c. That means your alpha p is actually 3 dB, right? So at that time omega p will be equal to omega c. That is the relevance of the term monotonic in passband. And anything else? Then if your design constraint is saying that you should meet the passband specifications, you should meet the passband, meeting passband specification. If you come across a term like that, that means while calculating omega c, you have to use the equation which involves omega p, that is omega p by epsilon raised to 1 by n. Just revise all those things. That's the design of IR filter. Last step, if it is low pass filter, you will replace s with s by omega c. That's it. Do remember, if the question is to design a high pass filter, very important, in the first step you have to convert the specifications of high pass to low pass, then only you should design low pass. At the last step you have to convert it back to high pass using the substitution s tends to omega c by s. So high pass aanu chodyamengil, first you have to convert the specification of high pass to low pass, then only you design the low pass filter. And specifically for high pass filter, the change will be omega p and omega s has to be interchanged. Okay, that's very simple in the case of high pass. Band pass, band stop we will do it later. Okay, so that's it. Fourth module of first topic. So you have designed analog filter. Now you can convert it to digital. You have two methods to convert it to digital. So to design digital filter, you have two methods. First one is the impulse invariance method, and second one is the bilinear transformation. Impulse invariance method, you have to express, to doing problems, I will tell you the method. You have to express it as the transfer function as h of s as sum of single order transfer functions, that is of the form ck by s minus pk, where pk is your pole, right? Then your answer will be h of z will be ck by 1 minus e raised to minus pk, e raised to pkt in z raised to minus 1, right? So that was your transfer function. You can directly do problems like that. The important thing you have to understand with impulse invariance method is, the concept is that the substitution that you are using is z equal to e raised to st. So actually we are replacing e raised to st with z, right? So this is the mathematical substitution that's happening behind this thing. So from this you should be able to prove that all the stable s-plane poles will be mapped to all stable s-plane zeros. You can replace z with r e power j small omega and s with sigma plus j capital omega. You can compare LHS and RHS and easily prove that. We have seen that. Next thing is, impulse invariance method has got a disadvantage. He is not able to design all the digital filters, right? The problem is you have some aliasing after say 2 pi by t. So you should be able to justify that thing also. Why impulse invariance method is not able to design say high pass filter or band stop filter and so on. So at higher, it's actually, the simple reason is it's a many to one mapping. Many points in the S-plane is mapped to single point in the Z-plane, that will cause aliasing. So you should be able to justify that by words and mathematically also. And the solution to all this thing is bilinear transformation. So bilinear transformation main disadvantage is it is a non-linear transformation, right? So it's linear with small values of omega, but at higher values of omega it is non-linear, and therefore you will have some distortions in the response, digital frequency response. Analog response, the shape you are expecting, that will not be available with digital, because their relation is non-linear. So that effect is referred as warping effect, and definitely we have a solution for that, that is pre-warping. So you pre-warp the given frequencies. See, given frequency implies you may be given some specifications, right? You may be given some digital specifications. Then you have to pre-warp it to the equivalent analog specification. Give importance to these words. When digital specification is given, first I have to design analog filter, so I need some analog specification. So if digital specification is given, you pre-warp it to equivalent analog specifications. Sometimes I'm giving importance to the term equivalent, because sometimes the question may be like this: for a digital filter with the equivalent analog specification in the analog specification direct eduthu tharam. In that case, you don't want to go for pre-warping, because analog specification may be given to you, right? So if digital specification is given to you, you have to do pre-warping and find the equivalent analog specifications. Then you have to design analog filter. At the last step, you apply bilinear transformation. Automatically pre-warping and warping will get cancelled. So then you have frequency transformation. That is actually how to convert low pass to high pass, low pass to band pass, and so on. So we have discussed only low pass to high pass. Forget the other things. I will give you the equations later. So that's the end of module 4. So 3 was design of FIR filter, 4 was design of IAR filter. Now back to module 5. This is completely realization of filters. Module 5 is completely realization of filters. First thing is you have to realize FIR filter and IR filter. We started with IR filter. IR filter, you have different methods. One is direct form 1 and 2. Okay. Then you have transpose structure also. Then mainly you have to focus on direct form 1 and 2, cascade form and parallel form, right? Direct form 1 will have separate delay tracks in the input and output. Direct form 2 will have a common delay track at the middle, so that you can minimize the number of delay elements. That's how you can compare direct form 1 and 2. Coming to cascade and parallel output of, you have to split your transfer function h of z as h1 into h2 into so on. Parallel means h1 plus h2 plus split here. Here you have to practice with partial fraction. Cascade form you have to practice with partial fraction. Parallel form you have to practice with division. Okay, you have to, sometimes you may have to perform division. So if the numerator coefficient is greater, definitely you have to, numerator power is greater than the denominator power, you have to go for division in parallel form. So practice mathematical division in parallel form, and partial fraction in cascade form. That is the mathematical practice that you want over there. Then coming to design of FIR filters, you will have first thing was tapped delay line structure, right? Tapped delay line structure. That was again divided as direct form and cascade form. Very easy. You will have simple track of delay element. From there, you have to do some tappings and add all those things. That was pretty easy. Direct form and cascade form. Lattice structure. It's again another important thing. You should be comfortable with the lattice structure. First order structure. You will have two rails, say F rail and G rail. You will have lattice coefficients K1, K2, K3. So you should be able to convert from lattice structure to direct form and direct form to lattice structure back. So you have to practice. You have to spend more time over here, lattice structure. Okay. And the probability of asking lattice structure is 50%. Most probably you will have this direct form and cascade form. Lattice structure ചോദിക്കാറുണ്ട്. എന്നിരുന്നാലും direct forms commonly ചോദിക്കുന്ന direct form ഒക്കെയാണ് എപ്പോഴും. Okay, so you can score 5 marks in 1 or 2 minutes with this direct form and cascade. And the last topic is TMS 320C67XX processor architecture. Two things you have to study. One is architecture. A second thing is its features. Okay, next class I will conclude. Just TI module. So TI data sheet I will conclude that. So that's it. That's the end of 3, 4, and 5 modules.